Multitasking cut AI agent completion rates from 16.7% to 8.7%. As concurrent work grew from 12 to 46 tasks, leading computer-using agents did not merely slow down. They forgot details, mixed contexts, missed dependencies, and had to reprioritize constantly. Microsoft Research built multi-horizon task environments for CorpGen, where an agent managed as many as 46 tasks over 5 to 6 hours, with each task requiring 10 to 30 dependent steps. This episode turns the 4 failure modes and the system responses into a multi-horizon task queue board for tracking dependencies, isolating memory, choosing the next action, and preserving evidence for acceptance. This video is packed with practical, high-value insights to help you get better at using AI. It's a longer one, so follow Tiny Agent and save it so you don't lose it. First, understand why multitasking is not the same as copying single-task performance dozens of times. Working memory fills rapidly when many active tasks each carry their own goal, state, files, and next action. Observations and instructions from one task can leak into another task's reasoning, producing a plausible action for the wrong context. Dependencies are not a simple chain. They form a web in which unfinished upstream work should make downstream tasks wait, reroute, or request information. Every execution cycle must compare priorities across all active work instead of blindly resuming the last task. Across 3 agent systems, raising concurrent load from 12 to 46 tasks reduced average completion from 16.7% to 8.7%. The bottleneck is therefore not just the base model. It is also the system's ability to manage plans, context, dependencies, and learning across cycles. Chapter Recap. First, multitasking overloads working memory. Second, context contamination and dependency webs create wrong actions. Third, every cycle needs a fresh priority decision. Next, build a hierarchical plan that connects the day's objective to one current next action. The top layer holds daily goals and hard deadlines, the middle layer holds task stages and dependencies, and the bottom layer chooses the current action. If every step rereads all 46 tasks, planning cost repeats and the loudest task can displace the dependency that matters most. A stronger design creates a daily plan, then lets each execution cycle load only the relevant task, runnable conditions, and blockers. Every queue item should record priority, upstream dependencies, current state, next action, and recent evidence instead of one vague in-progress label. When upstream work completes, the system wakes affected downstream tasks. When dependencies remain unmet, it must not guess the missing result. At the end of each cycle, write back evidence and state, then compare deadlines, impact, newly removed blockers, and switching cost before choosing the next item. Chapter Recap. First, separate objectives, stages, and actions. Second, load only the relevant task and dependencies for each cycle. Third, write back results before reprioritizing the queue. The third step is isolating task context and using tiered memory to reduce interference while preserving continuity across hours. Complex research or computer operations can run in subagents with isolated contexts, then return structured results to the main queue. The goal is not more agents. It is preventing one task's dense detail from contaminating another task's decision. Working memory keeps only information needed for the current action. Structured long-term memory stores task state, decisions, and outcomes, while semantic memory stores reusable experience. Routine observations can be summarized aggressively, but permissions, errors, dependency changes, and acceptance evidence need high-fidelity retention. Retrieval should filter by task identity and current stage before adding related history, rather than pushing every prior trace back into context. A handoff must include the goal, completed work, unverified claims, blockers, next action, and evidence location so a new cycle can continue without rediscovery. Chapter Recap. First, isolated contexts prevent cross-task interference. Second, tiered memory stores different information for different purposes. Third, evidence-rich handoffs preserve continuity across cycles. The fourth step is turning successful trajectories into reusable experience and accepting work from real outputs rather than screen activity. CorpGen added orchestration, cognitive tools, and then experiential learning. The learning component produced the largest gain, raising completion from 8.7% to 15.2%. Reusable experience is not a full conversation. It captures triggers, critical steps, tool choices, recovery paths, and acceptance evidence for structurally similar work. When a new task arrives, retrieve a similar successful pattern, then adapt it to current permissions, data, and dependencies instead of replaying an old trace. Evaluation method changes the result. Real output files agreed with human judgments about 90% of the time, while screenshots and action logs agreed only about 40% of the time. What an agent did is not the same as what the task completed. Final state, file content, and reproducible outcomes are the primary evidence. The best reported completion was still only 15.2% in a controlled environment, so this research does not prove that real enterprises can run these systems unattended. Chapter Recap. First, experiential learning stores transferable success structures. Second, real outputs align with task results better than activity traces. Third, the improvement is large while absolute completion remains limited. Now compress the method into a queue board that can be reconsidered after every execution cycle. The first field records the task and intended result, including owner, final state, and hard deadline rather than just an action name. The second field records upstream dependencies and runnable conditions, including files, approvals, data, or another agent's result. The third field records current state, next action, and recent evidence so recovery begins from known facts and unverified claims remain visible. The fourth field records the memory layer and isolation strategy, active context, long-term memory, or an isolated subagent. The fifth field records priority signals such as deadline, impact, newly removed blockers, risk, and switching cost, recalculated after new evidence. The sixth field records the acceptance object, favoring final files, system state, and human judgment over screenshots or action logs alone. Take a screenshot of this queue board and use it directly. Chapter recap. First, queue the intended result and dependencies. Second, refresh state, evidence, and priority every cycle. Third, accept work from the final environment state. In summary, AI agent multitasking fails not only because models are weak, but because single-task planning and memory cannot absorb a constantly changing dependency web. Use hierarchical planning to choose the current action, isolated context and tiered memory to reduce interference, and experiential learning to reuse successful structures. Then verify real files and environment state so the queue records what the task completed rather than how busy the agent looked. If your AI agent runs several tasks at once, which problem would you solve first? Memory interference, dependency weighting, or reprioritization? Share it in the comments. Follow Tiny Agent. Tiny Agent helps you get better at using AI.